In this video, we are going to look at ionic bonding and metallic bonding. Because in the last video, we looked at covalent bonding. So today we are going to finish off with chemical bonding and finish off with term 1's work. Ionic bonding, it is a type of chemical bond where one or more electrons are transferred from one atom to another. So now we are no longer talking about the sharing of electrons, but we are talking about the transfer of electrons from one atom to another. When ionic bonds form, a metal donates one or more electrons. Remember, metals are found on the left of the periodic table, so they tend to lose electrons, so they donate electrons due to having a low electronegativity to form a positive ion, a cation. The non-metal ion has a high electronegativity. Non-metal ions or non-metal elements are found on the right side of the periodic table, and they tend to gain electrons to form negative ions or anions. The two ions are then attracted to each other by electrostatic forces. So nonmetals and metals, they are attracted by electrostatic forces and they form the best bonding, since the one loses electrons and the one gains electrons. Let's look at examples. Example number 1, we will look at the reaction between sodium and chlorine. So sodium is in group 1, and its electron configuration, as you can see in this picture, is 1s2, 2s2, 2p6, 3s1. So in the outermost energy level, it has only one electron, and chlorine has 7 electrons in its outermost energy level because it is in group 7. So what happens then? We see the diagram or the representation of the energy levels and the electrons. So we have N1, which represents the first energy level, which only has 2 electrons. It only occupies a maximum of 2 electrons. And then we have the second energy level, which carries 8 electrons in total, and the third energy level, which also carries 8 electrons in total. And for sodium, the third energy level carries only 1 electron because the outermost valence electron is only 1 for sodium, since it's in group 1. And then for chlorine, we see that the third energy level carries 7 electrons. So sodium needs only 1 electron to complete its outermost energy level, which is the third energy level. And sodium, since it has 8 electrons already in the second energy level and only 1 in the third energy level, it is much more easier for it to lose this 1 electron and to stay filled in the second energy level. So sodium is like, okay, chlorine, fine, I'm gonna give you my electron since you need the electron, and it's very hard for me to gain 7 electrons, so I'm just gonna give away my electron to you. So I will stay filled on the second energy level. So sodium does that, and then there becomes an attraction between the sodium ion and the chlorine ion, and sodium becomes positively charged and chlorine negatively charged, and they form sodium chlorine. You know sodium chlorine, table salt. According to above electron configuration and Bohr models, I hope you do remember Bohr models. We did Bohr models when we did the atom. It is clear that sodium has 1 valence electron and that chlorine has 7 valence electrons. So if sodium atom and chlorine atom make contact, the sodium atom donates its valence electron to the chlorine atom, and they form sodium chloride. That is how we form our table salt. So the ions combine in a crystal lattice through electrostatic forces of attraction. If we look at the Lewis structures for both sodium and chlorine, we have 3 steps at which these attraction occurs. So the first step, we have sodium giving away its electron. So sodium has 1 electron and it decides to give away that electron to become positively charged. And chlorine gains an electron. So the second step is chlorine gaining an electron and it becomes negatively charged, as you can see in the second step. And then the third step is the positive charge of chlorine and the positive charge of sodium, my bad, and the negative charge of chlorine. They both combine to form a neutral charge, which is a neutral compound, which is sodium chloride. We know that positive charges and negative charges attract, right? So this is why the sodium ion and the chlorine ion attract, because sodium is positively charged and chlorine is negatively charged. So when they combine, they form a neutral compound, which is sodium chloride. Let's move on to another example of magnesium and chlorine. So magnesium is in group 2 and chlorine is in group 7. So when they combine, a magnesium atom can donate its 2 valence electrons to 2 chlorine atoms. So because magnesium has to lose two of its valence electrons, it needs 2 molecules there of chlorine so it can donate the valence electrons to it. Well, magnesium can also react with a nonmetal that actually needs 2 electrons to fill its outermost energy level, like oxygen. But here let's just look at magnesium reacting with chlorine. So then the form ions pack as follows in the crystal lattice. So as you can see on the diagram below, the chlorine, the 2 chlorine atoms, they are attracted to the magnesium ion. The magnesium ion has a charge of positive 2. So each chlorine atom has a charge of -1. So if these combine, they form a neutral compound, which is MgCl2. I hope you understand. I hope I'm not confusing you. And then the Lewis structure. How does this actually happen? So magnesium has 2 valence electrons and it decides to lose these valence electrons so it can acquire the octet structure, or the structure of the nearest noble gas. And then the 2 chlorine atoms, they also gain 2 electrons, so each chlorine atom gains 1 electron, and then when these combine, they form a neutral compound, which is MgC2. Now let's look at the crystal lattice structure of ionic compounds. So ionic compounds tend to form a crystal lattice arrangement. A crystal lattice is the arrangement of ions in a regular geometric structure. As you can see in the structure below, the structure with purple and green atoms. So the green atoms are chlorine atoms, and then the purple ones are sodium ion atoms. So sodium chloride does not contain 1 sodium and 1 chlorine ion, but rather a lot of these 2 ions arranged in a crystal lattice where the ratio of sodium to chlorine ions is 1:1. So our table salt is not made up of just 1 sodium and 1 chlorine, but it is made up of many sodium and chlorine ions combined together to form a crystal lattice like the one you see below. Now let us look at metallic bonding. So metallic bonding is the electrostatic attraction between the positively charged atomic nuclei of metal atoms and the delocalized electrons in the metal. Metal atoms are arranged in a close packed orderly pattern like a crystal lattice, like the one we saw on the previous slide. As a result of the densely packed atoms, their valence orbitals overlap with each other, and the outer orbitals contain few electrons with low energies, so they become detached from the atomic nuclei and delocalized, so they just wander around the atomic nuclei. We say a sea of delocalized electrons forms between the positive nuclei or cores. Strong electrostatic forces of attraction are formed between the positive atomic nuclei and the negative electrons. So the electrons that wander or move around the atomic nuclei form a strong electrostatic force. The free moving electrons also act as energy carriers and are responsible for the conduction of electrical current in metal conductor. That is why metals are very good electrical and thermal conductors. This is because they have these delocalized electrons that act as energy carriers of electricity. Atomic layers can also move across each other, and that explains why metals are malleable and ductile. So this is an example of what I was talking about. We have the positive atomic nuclei, and it is surrounded by localized electrons. As you can see, the electrons are actually moving around these atomic nuclei. And the diagram on the right is a ballistic model of copper. It is the result of these delocalized electrons around the positive atomic nuclei. So at the end, we get structures like this, structures that are packed together as a result of these delocalized electrons moving around the atomic nuclei. So this is the summary. You can go over it yourself. The summary of covalent bonding, ionic bonding, and metallic bonding. Just remember that covalent bonding is between non-metal atoms, and we get sharing of electrons, and then ionic bonding, it is between a metal and a non-metal, and we get transfer of ions or electrons. And then metallic bonding is between metal atoms, and we get delocalized electrons moving around an atomic nuclei, positive atomic nuclei. So let's do a little bit of revising names. Do you still remember how we name compounds? Use the position of an element in a group to determine its valency. So to determine the valency for metals from group 1 to 3, the valencies are 1 to 3, so it's basically just the group number. For non-metals from group 5 to 8, you say the group number minus 8. Then you should get to know the most common valencies of the heavy transition metals and learn names and formula of valencies of the polyatomic ions. We did this a long time ago. Remember that if in the formula the cations always come first, so when you write the formula of the compound, you always start with the cation and then you write the anion second. And then covalent bonding, we've already talked about covalent bonding and how it occurs and when it occurs. So the number of bonds that is formed is dependent on the valence of the elements. We already did that, the single bond, double bond, and triple bond. In compounds with oxygen, sulfur, and the halogen atoms. Remember, halogen atoms are your group 17 or group 7 elements. The elements hydrogen, carbon, nitrogen, and phosphorus are usually written first in the formula. Okay. The number of atoms of the kind, specifically the number of oxygen, sulfur, and halogen atoms, is usually indicated by a prefix. So I hope you do remember the prefixes that we did: the mono, the tri, the bi, the tetra, etc. Remember relative molecular and formula mass. You should also know that. So when elements combine covalently, small molecules are formed, and ionic bonding leads to forming of ionic crystal lattices or formula units. So in molecules like carbon dioxide, water, ammonia, the mass of the molecule is called the relative molecular mass. And how do we find this relative molecular mass? It is calculated by multiplying the relative atomic masses of each kind of atom with the number of atoms in the compound and then adding it up. So for example, the relative molecular mass of water. So in water, we have 2 hydrogen atoms and 1 oxygen atom. So you go to your periodic table and look at the atomic masses. So you have the atomic masses in the periodic table, and you will say 2 because we have 2 hydrogen molecules times by 1. 1 is the atomic mass of hydrogen. And then you are going to add that to 16. So we have only 1 oxygen molecule, so you don't really need to multiply by the 1. So you are going to say 16, and then you are going to get 18. And then for carbon dioxide, we have 1 carbon atom in carbon dioxide, and we have 2 oxygen atoms. So you are going to say 12. 12 is the atomic mass of carbon from the periodic table. Then you're going to add that to the product of 2 and 16. 2 is from the fact that we have 2 oxygen atoms, and then the 16 is the atomic mass of oxygen, and then you get the answer of 44. Okay, and then we also have a relative formula mass. So how do we calculate the relative formula mass? To get the relative formula mass, you get it from adding also the relative atomic masses. So for example, sodium hydrogen carbonate NaHCO3 contains 1 atom of sodium, 1 atom of hydrogen, 1 atom of carbon, and 3 atoms of oxygen. So you are going to say 23. 23 is the atomic mass of sodium, plus 1, which is the atomic mass of hydrogen, plus 12, which is the atomic mass of carbon, and then you're gonna add a product of 3 and 16. Where does the 3 come from? It comes from the fact that we have 3 oxygen atoms, and then you're going to get a total of 84. So molecular mass and formula mass are actually the same, but they are just used to distinguish between the kind of bond and product form, but all in all they are calculated the same. So formula mass is for ionic bond. So if there is an ionic bond, then we call it a formula mass. And molecular mass, molecular mass, it is when we have a covalent bond. So that is the only difference between formula mass and molecular mass. They are basically the same thing, but formula mass is for ionic bonding and molecular mass is for covalent bonding. That is it for this video, and that is it for Term 1's work. It ends here. Thank you.